So whenever we want to do an ionic equation, we first need the molecular equation. And we're going to have a look at this example here, the reaction between iron chloride and sodium hydroxide. So we know this is an example of a double displacement reaction. And for those of you who are unable to identify what kind of reaction this is, I have made another video which you can have a look at in the description down below. So in order to work out the products of this equation, we know that because it's double displacement, we need to swap around the cations and the anions of both of these molecules. So our products will be iron hydroxide and sodium chloride. And when we balance this up, we know we need a 2 around here, as well as a 2 around the sodium chloride. And that's our equation there. Now, we just need to work out the state symbols of our products. Because we know iron hydroxide is a hydroxide and most hydroxides are insoluble, we know that this is going to be a solid, and we know that sodium chloride or table salt is soluble in water, so this is going to be aqueous. Next, we're going to split up all the molecules into the cations and anions, but only the aqueous molecules. So the molecules which are all aqueous, we're going to split them up into their cation and anion forms. And if we were to do that for the first molecule, iron chloride, we know that it's made up of iron 2+, as well as chlorine ions. However, because it's FeCl2, we know we need to put a 2 in front of the Cl-. And we're going to continue the cycle. So plus 2 Na+, plus 2 OH-, and the reason I'm putting 2 is because we have 2 NaOHs altogether, so that means we must have 2 of these individual ions. Now, I've run out of room, so I'm going to do the products down here. Next, I need to have a look at the ions for sodium chloride. I have to skip iron hydroxide, and the reason I'm doing that is because it is not aqueous, it is insoluble. So if I were to split up NaCl, I will split it up into 2 Na pluses and 2 chlorines. And I'll just have the solid iron hydroxide left over. Now that I have this, I have a whole equation which I can see represented as split ions. So I have a whole equation which I've split only the aqueous ions here, here, and here. Now what I can do is I can see the spectator ions. And what I mean by that is what 2 ions are similar on this side, on the reactant side, as well as over on the product side. Well, I noticed that Na plus and Na plus are the same. So in other words, they just spectated in this equation. So they didn't really partake, so I'm just going to cancel out the Na pluses. And the chlorines also did the same thing, so I'm going to cancel out the chlorines. And these ions are called spectator ions because it looks like they did something in the reaction, however they just spectated and took some of the credit. So now my ionic equation is whatever I have left over. And what I have left over is the Fe2+, the OH-, as well as the iron hydroxide solid itself. So my final ionic equation would be Fe2+ plus 2 hydroxides forms iron hydroxide in its solid form. So let's have a look at another example between an acid and a base. In this example, we need to work out what the products will be. And because we know this is a reaction between an acid and a metal carbonate, we know a reaction between those two. will form acid plus metal carbonate, will form a salt plus water and carbon dioxide. And the way we can work out what the salt is we can take the anion of one of these substances. So the metallic anion is the sodium, and the non-metallic anion of the other substance, which in this case is the ethanoate ion. So if I were to draw the products, I would simply have NaCH3COO, and we know all ethanoates are aqueous, plus water in its liquid form, and plus carbon dioxide. And now we have to balance. And judging from the look of it, it does look pretty balanced. And now we have to balance it. So in order to balance this equation, I'm just going to do 2 in front of the product salt and a 2 in front of the acetic acid. And that looks pretty balanced to me. Now I'm going to split up all the ions. Now I'm going to split up all the molecules into its ionic forms. So everything that's aqueous, which is this here, the acetic acid, as well as the sodium acetate, I'm going to split them up into their ions. So the sodium carbonate, you can split up into Na plus and acetic and carbonate. However, just remember, you need to have 2 of these sodiums because there is a 2 in next to the sodium. Then I'm going to do the same thing with the acetic acid. So CH3COO minus plus H plus, remembering to put a 2 in front of both of them because there's 2 of the whole molecule. And now I'm going to do the same thing to the product side. On the product side, I will simply have 2 Na pluses as well as 2 ethanoates, so 2 CH3COO minus, and we're going to leave the water and carbon dioxide as is because those aren't aqueous. Now, I've run out a bit of room, so just remember these are our products and these are our reactants. So what 2 ions can you see, or what ions can you see that are the same in our reactants and our product side? Well, I can already see a sodium ion here and a sodium ion here. And I can also see the acetate ion or ethanoate ion, depending on where you're from. And what I'm left with is just the carbonate ion, the hydrogen ion, water, and carbon dioxide. So that is my ionic equation. CO32 minus plus 2H plus forms water as well as carbon dioxide gas. Now let's have a look at this example here. We have silver nitrate plus sodium chloride. Again, this is another example of a double displacement reaction. So all we're going to do is we're going to swap around the cations and the anions, and the cation with the anion. So our product will simply be silver chloride and sodium nitrate. And we know that silver chloride is an insoluble precipitate and sodium nitrate is aqueous. Most things with sodium as a cation, are soluble. So now we're going to repeat the same steps. We're going to take all the aqueous species and we're going to split them up into their ions. So silver nitrate, we can split up into silver ions as well as nitrate ions. And NaCl, we can split up into sodium ions and chlorine ions. And this forms, we keep the silver chloride because it's a solid and we only split up aqueous species, plus Na plus in its aqueous form, and NO3 minus in its aqueous form. So now that we have all these ions together, we have to see which two ions or which ions are the same on the left as well as on the right. So I can already notice that we have a nitrate ion on both sides, and because the nitrate ions are the same as on the reactants and the products, it means it didn't really participate. So now we have cancelled those two, and I can also see a sodium ion that I can't get rid of. So now what we're going to be left with is our Ionic equation. We can be left with our silver, chlorine, and silver chloride. And that is our Ionic equation. Now let's have a look at an example where we're going to have a diprotic acid. Well, we know that this is a reaction between an acid and a base, and more specifically, we know it's a reaction between an acid and a metal hydroxide. And the reaction here will simply form a salt plus water, and that's it. And we know in order to work out what the salt is, we have a look at the metal cation, and the only metal cation we can see here is the barium, and therefore the non-metal anion of the other molecule, which in this case is simply the sulfate. So our salt is going to be barium sulfate. And we know that barium sulfate is an insoluble salt. And we just add water to this. Now, to balance it up, now we have to look at our aqueous species and once again split them up into their individual ions. So I'm going to take the sulfuric acid step first. We can split up sulfuric acid into H plus ions as well as sulfate ions. And we need to remember that although yes, we have hydrogen and sulfate ions, we also need to remember that we have two hydrogen ions. So we need to remember to put a 2 in front of the H plus. Then we can split up the barium hydroxide, and we had barium 2 plus and hydroxide ions. And we know because we have a 2 next to the OH, we have to put a 2 out here as well to say that we have 2 hydroxide ions. And now that we have this equation here, we can do the products. We don't have to split either of the two products, and that's purely because we don't have anything that's aqueous on that side. So now we have to get rid of our we have to get rid of our spectator ions. And right now, I don't notice any aqueous ions. And right now, I don't notice any ions which can be a spectator ion. So the correct answer to this question is you leave the molecular formula as is. Now, in this example, you can see that we've split up all our ions. However, we have been unable to cancel out any of these ions with the ions on the opposite side because there are no spectator ions. If you're in a situation where there are no spectator ions, what that simply means is the original molecular equation is also the ionic equation. So our ionic equation is simply what we had off before. So next time when you're doing a question, make sure to inspect the reactants and the product side, and also the product side, to see if there's anything aqueous. Because if there is nothing aqueous here, then the chances are you are going to have no spectator ions.